Okay, so welcome to the fourth lecture. So this deals with the second half of chapter 2, 2.4, 2.5, 2.6, and the topic is Gröbner bases and tropical bases of ideals. So we're going to assume that K is a field with a valuation, and we're going to assume that the valuation has a splitting. So this will be automatic if K is algebraically closed. But if K is not algebraically closed, we actually have to assume this. So splitting is a group homomorphism from the additive group of valuations, the value group, into the multiplicative group K star, which takes W to T to the W. So we're going to assume that this exists. Now then we also get, from this data, we get a homomorphism, a multiplicative homomorphism, from K star to little k star. Right? So we get a multiplicative homomorphism, and this multiplicative homomorphism takes a field element in the big field and it maps it to T to the minus the valuation of A times A bar. Okay, so that's an element of the small field. So in English, you take a Puiseux series and you look at the lowest coefficient you see. Okay? But this works over any field under these hypotheses, but we need that there's a splitting, right? And that's given here by this T to the minus well A. Okay? And this is actually a multiplicative homomorphism. So if you take the lowest coefficient of a product of Puiseux series, it's the product of the lowest coefficients. It's a multiplicative homomorphism. So the goal, the first goal now, is to develop the theory of Gröbner bases for homogeneous ideals. And these are going to be homogeneous ideals in a polynomial ring in n plus 1 variables, x1 up to x0 up to xn, and I'm going to use the notation sometimes S sub k. Polynomial ring in n plus variables, n plus 1 variables, describing projective varieties in Pn. Now there's an ominous sentence in the book at the beginning of section 2.4. It basically says, buckle your seatbelt. Right? It says, even if you think you know Gröbner bases very well, you are in for a rough ride. Right? Because we're going to redevelop Gröbner bases, but not in the way you're familiar with them, from Coxeter-O'Shea or from symbolic computation, but we're going to do something quite different. We're going to incorporate the structure of the valued field and everything that comes with this. Okay? So how does this go? Well, suppose you have a polynomial f, so sum cu to the xu, so it's a finite sum over non-negative integer vectors u. That's a polynomial in Sk, maybe homogeneous, maybe not. So for such a polynomial, we define its tropicalization by replacing the arithmetic operations by the tropical operations and by replacing the coefficients by their valuation. Okay, so tropicalization is a tropical polynomial, so it's a function from R n plus 1 into R. And in classical notation, it's given as the minimum of a finite list of affine linear functions. So the coefficient gets replaced by its valuation. And then W dot U, right, that's the linear form coming from the monomial. And then this minimum is over all non-zero U. That is to say, all terms that actually appear. Actually, I guess Cu non-zero. All U such that Cu is non-zero. Okay? Now, with this in mind, for any W in Rn plus 1, for every W in Rn plus 1, even though its coordinates may not be in the value group, we can still define the initial form. We can define the initial form. In W of f, And this initial form is in the polynomial ring S little k. It's in the polynomial ring over little k in n plus 1 variables, x0 up to xn. Now I wrote can define, I didn't give you the definition. And I will not give you the definition because you can read the definition in the book. I'm going to give you a simpler definition. That's good enough. But it can be defined, but it's a little bit technical. Let me give you the definition in a simplified version. If it so happens that the coordinates of W are in the value group, right? So if W is in gamma to the n plus 1, then the initial form can be defined as follows. Then the initial form of f is t to the power minus the tropicalization evaluated at W times the polynomial t to the w0, x0, blah, blah, t to the wn, xn, blah, blah, and the whole thing barred. Okay? So this is a little easier. So what am I doing? I'm taking my classical polynomial and I replace xi by xi times t to the wi. T to the wi is defined because wi is in the value group and because there's a splitting. Right? Because there's a splitting, this is actually defined. Okay? Now I can multiply this by t to the minus. This element is certainly in the value group, right? I can multiply this. So then the result of this is going to be a polynomial x0 up to xn whose coefficients are in k. Right? Fair enough. But this has a non-zero in each term. I mean, there will be a non-zero term in the valuation, and then you pass to the residue ring. So this is a polynomial in x0, x1 up to xn over little k. That's the initial form. Now, why is this hard? Why did I talk about buckle your seatbelt? Well, because in the familiar Gröbner basis theory, you have a notion of a monomial ordering. Right? There's no, the coefficients are sort of boring, right? They're real numbers, they're rational, whatever they are, but the coefficients don't really contribute to sorting the terms. Here, there is no monomial ordering. There's never monomial ordering. It's the field and the valuations that drive the ordering. Right? So the ordering on monomials and the choice of initial forms is driven by the structure of the valued field and everything that comes with it, such as the little field. Okay? That's why it's buckle your seatbelt. Okay, so that's the initial form. Well, with this definition, if I is a homogeneous ideal, classical homogeneous ideal in the polynomial ring Sk, then it has an initial ideal. So the initial ideal is generated by the initial forms. So the initial ideal in Wi is defined to be generated by in Wf and then over all infinitely many polynomials f in the ideal. Right? So again, if W, the coordinates are in the value group, then this simple definition does it. If some coordinates of W are not in the value group, you need a slightly more technical definition, which I spared you from. Now, what's a Gröbner basis? Well, before defining that, let me be clear, right? This is in S little k, right? Because these initial forms have their coefficients in the residue field, right? Because this thing is in, should have written this, is in Sk because of the bar. Now, a Gröbner basis by definition is a finite set that suffices here. So it's a set G, a finite set. It's called the polynomials G1 up to Gs in I. And if I is a homogeneous ideal, I might as well assume that these GIs are homogeneous. But the decisive condition is that the ideal generated by the initial forms, so initial of G1, blah, blah, initial of Gs, that generates the initial ideal. And just for clarity, so this takes place over the little field. Okay? That's the definition of a Gröbner basis. So it's the usual definition of Gröbner basis. It's the usual definition of initial ideal, but the initial form is a little subtle. There is no term order. Right? The ordering is driven by the field and by the valuation. That's very important. So remark. 244 is that here we're using that I is homogeneous. So since I was to be assumed to be a homogeneous ideal, G actually generates the ideal. Right? So if you have a Gröbner basis, so if the initial forms in the polynomial ring over the small field happens to generate the initial ideal, then it follows from homogeneity that G upstairs generates the ideal that you start with. Let's see an example. That's 2, 4, 3. I do understand that this is a little hard now. Right? So this is the first hard section in the book, is 2.4. It's unfamiliar even to those who have studied Gröbner basis, and it's hard not just because it's 38° Fahrenheit centigrade out there, it's just a little tricky. So it is recommended, as always, to read the relevant chapter of the book before coming to the class or before watching the video. Okay, so example 243, so let's take the rational numbers with the two-adic valuation. The residue field is the field on two elements. Let's just take the ideal of a line in P3, so x0 plus 2 x1 minus 3 x2, 3 x1 minus 4 x2 plus 5 x3. Right? So this is just a linear ideal in a polynomial ring in 4 variables over the rational numbers. Okay? So let's calculate the initial ideal, and let's take the weight vector to be 0, 0, 0, 0. Okay? So let's calculate the initial ideal of this with respect to 0, 0, 0. Now that vector certainly has its coordinates in the value group. So that's that. So then the two generators, I claim, are a Gröbner basis. Right? You check that these two generators happen to be a Gröbner basis if W is the 0 vector and we use the two-adic valuation. And the initial ideal. Now the initial ideal is an ideal in a polynomial ring in the same variables over the two-element field. Right? The coefficients are now in the two-element field. And it's generated by the leading forms x0 plus x2 and then x1 plus x3. Right? So this first polynomial, so this polynomial with rational coefficients has initial form x0 plus x2. Well, because this term 2x1 is high, it goes away, right? Because this has a higher two-adic valuation. So the lowest terms are x0 minus 3x2. But we have to map the coefficients by the bar. We have to map the coefficients into the residue field. Right? So the image of minus 3 in the residue field is 1. Right? So all we remember is these are odd or even. Right? So by the same token, so 3 is odd, 4 is even, 5 is odd. The initial form here is x1 plus x3. Okay? It is not so difficult, but it requires practice, right? And especially those who are familiar with Gröbner bases with the term orders need to rethink a little bit. However, having said that, everything does generalize the familiar Gröbner basis theory. So this generalizes the familiar Gröbner basis theory that you are familiar with, or with term orders. And there are 3 references that are given in the book. So There's a reference to Eisenbudt's textbook on commutative algebra with a view towards algebraic geometry. I wrote a little booklet that was published in '96 called Gröbner Bases and Convex Polytopes, and then last but not least, Cox-Lochet. Right? So the familiar Gröbner basis theory that you know from these and many, 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 many other sources is a special case as follows. We'll see an example. So you have familiar notions, such as Hilbert functions. What you do need at some stage is primary decomposition. Will come in handy next time of polynomial ideals, say the initial ideal. And from Eisenbutt, we know there's a tight connection between Gröbner basis and flatness, right? So the degeneration from the ideal to its initial ideal is a flat family, and in fact, the Eisenbutt introduces Gröbner basis in this manner. So all of this is true in this setting. Okay. So that was 2.4 Gröbner bases. So Gröbner basis gives you the definition of a Gröbner basis. It talks about initial forms and initial ideals. And the novelty here is that it's the valuation that drives the ordering. Now, getting more into polyhedral geometry, let's talk about Gröbner complexes. Right? I gave you a whirlwind non-introduction to polyhedral geometry, section 2.3. I just listed a few keywords and encouraged you to read up on this. So now we're going to apply this in this context. So let's define the following set. So I'm given an ideal I as before, homogeneous ideal in a polynomial ring and n+1 variables over a field with valuation, and W is a vector in Rn+1. So then this is the set of all W prime, all other vectors in Rn+1 that do the same thing to the ideal. Right? So this is the set of all W prime that select the same initial ideal. So I have an initial ideal, I have an ideal, you have a weight vector, and then we look at all W primes, all other weight vectors that pick the same initial ideal. So that's a subset of Rn+1. Now, what kind of subset is? Well, I claim that's a convex polyhedron. So that's a convex polyhedron in Rn+1. It may be bounded, might be a polytope, but it need not. But in any case, it's a rational polyhedron. It's a gamma-vel rational polyhedron. Right? So the description of this polyhedron or polytope doesn't use any old real numbers. It uses rational numbers, and being rational now means being in the value group. And in the Puiseux series, say, or p-adics, these are the usual rational numbers. It's a gamma-vel rational polyhedron. Another important property that this has, that always the linearity space always contains the line generated by the all-one vector. So this is a very important vector in the book. The all-one vector is the vector of length n+1 whose coordinates are 1, 1, 1, 1, 1, column vector. So this is the line generated by that vector. Okay? And that's because if some weight vector, you can always add the same constant here. That's because I is a homogeneous ideal. Since I is a homogeneous ideal, adding the same constant to every weight makes no difference. Then we have the following theorem, 2, 5, 3. So these polyhedra fit together nicely. So these polyhedra CIW for fixed I, as W varies over n+1 space, they fit together nicely. And fit together nicely means it's a gamma-vel rational polyhedral complex. So it's a finite collection of convex polyhedra, some bounded, some unbounded, and fit together nicely means that the intersection of any two is also in the family. And the way we're going to organize this, that the support of this is the entire space, but we're going to mod out by the lineality. So it's an Rn plus 1 mod the all 1 vector. Okay? So there's really a natural n-dimensional space, and this n-dimensional space is very important in the book. So it's Rn plus 1 modulo tropical scalar multiplication. That is to say, classical scalar addition. That is to say, mod the all 1 vector. Okay, so this is this says if I have a homogeneous ideal I, then there is a rational polyhedral complex supported on the entire space. And this is the Gröbner complex. of I. Okay. So every ideal defined over the field with valuation comes as with own decomposition of this n-dimensional space, and this decomposition is the Gröbner complex. Let's see an example. And maybe we'll do the example on the left side. So let's take a principal ideal in two variables. So this is example 2, 5, 9. So in this example, n is equal to 2, and k is the Puiseux series. And let's pick a polynomial that's a quadratic polynomial. So it's t x squared plus xy plus t y squared plus xz plus yz plus t z squared. So it's a homogeneous quadratic in 3, that is to say n plus 1 variables, and the ideal is simply the principal ideal generated by f. Right? So the variety is a conic in the projective plane. Now in this case, the Gröbner complex, sigma I, has 19, which is 6, plus 9 plus 4 cells. Okay, so there are 19 faces to the Gröbner complex. The Gröbner complex lives in a two-dimensional space, namely R3 mod R1. Okay? Now the way I'm going to draw in R3 mod R1 is that whenever I have a vector in R3, I can scale to have the last coordinate 0, for example. So I normalize it so that the last coordinate is 0. So by tropical scalar multiplication, right? So let's say you have a point in 3 space like with coordinates 7, 5, 2. Then you tropically multiply this by -2, right? Then you get 5, 3, 0. And I'm going to plot the point 5, 3. Okay? That's how I draw in this space. And then I get the familiar picture. Right? So then I get this picture of a subdivision given by the tropical conic. And this picture lives in R3 mod R1 with the convention that I indicated, that for any vector I draw the representative that has the last coordinate 0. Okay? Now this one has 19 cells, right? There are 6 two-dimensional cells, all unbounded here. There are 9 edges, 6 unbounded, 3 bounded. and then there are 4 vertices, right? Now the unbounded, the two-dimensional regions, they correspond to initial monomial ideals. Okay. So algebraically speaking, this principal ideal has 19 distinct initial ideals. One for each cell, right? Cells have dimensions 0, 1, or 2, so there are 19 distinct initial ideals. This ideal is defined over the big field, which is Puiseux series, but the initial ideal are defined over C, right? Because over the residue field, and each cell, gives you an initial ideal. So for example, I guess if we're out here, if we have very, very negative weights, right? So then over here, if W is chosen here, then the initial ideal will be that given by, let's see, so here W would be maybe -1, -1, 0, right? And that selects the initial ideal x squared plus y squared, which is over the little field C of x, y, z. Right? So, and then, oh, I'm sorry. No. This picks the z. Sorry, this picks the monomial ideal z squared. Okay. There are 6 monomial ideals, and then these lower dimensional cells, they pick non-monomial ideals. Now, corollary, important corollary, is 2, 5, 12. If I has constant coefficients, then something is the case. Constant coefficients means that you have a generating set of the ideal such that every coefficient of every generator has valuation 0. Okay? So the only valuations you see are 0. Now this might happen if the field itself has trivial valuation. So if you start with the field with the trivial valuation, that is to say where the value group is just 0, then that's the case. Right? So if your coefficients are just complex numbers, then there's no valuation. That's a constant coefficient situation. And then this is still meaningful. So in that case, the Gröbner complex is equal to the so-called Gröbner fan. So in that case, it's a fan, a finite collection of convex polyhedral cones emanating at the origin and fitting together nicely. And this is the Gröbner fan of I up to sign. There's always a convention whether you should work with min or max, and here we chose the min convention. And this theory of the Gröbner fan really was one of the things that was studied in depth in this little booklet called Gröbner bases and convex polytopes. So we knew many, many years ago that homogeneous ideals have a Gröbner fan, and therefore there's a piece of software called G-fan. So the original software for dealing with tropical geometry and calculating tropical varieties was based on the Gröbner fan, software written by Anders Jensen, and that's called G-fan, and G-fan stands for Gröbner fan, and Gröbner fan is the Gröbner complex in the constant coefficient case. So this corollary says that this really generalizes familiar concepts. Okay, so what have we done? We've talked about Gröbner bases, 2.4. We talked about its sort of polyhedral geometric rendering, the Gröbner complex, 2.5. And now let's talk about tropical bases. That's 2.6. Now let's shift gears. So I had assumed so far that the polynomials were given are homogeneous polynomials in n plus 1 variables defining a projective variety, such as this conic. But now let's work with Laurent polynomials. In 2.6, it's more natural to go back to the setting of Laurent polynomials. So I'm going to write k of x plus minus for the Laurent polynomial ring in n variables, x1 up to xn, polynomials with negative integer exponents allowed. Now we can certainly define the initial form of any Laurent polynomial as before. Right? So if you give me a Laurent polynomial, I can run the same definition that we had before. Well, there's the definition, where wi is not in the value group that I spared you from, and then there's the other one that you saw, and you can also do this for ideals. Right? So there's certainly a well-defined notion of initial form, initial ideal, and these objects, as before, will be in the same ring, but now with coefficients in the little field. Right? So this extends, for this part we do not need homogeneous ideals. For this we can work with Laurent polynomials, an ideal of Laurent polynomials. But what's different? What is different here? Right? There's an important difference. There's a very, very important difference. Well, what's in W of I? Well, let's suppose W is sort of random, right? So you pick the coordinates W1, W2 at random, right? They're like 2, 7, minus 5 over 4, whatever, right? You pick some random Wi, and you take a Laurent polynomial. Then the initial form will be a monomial, right? Because there's only one term that has the lowest weight. So the initial ideal will be generated by monomials. Now, why is that a big deal? Well, because monomials are units, right? In a Laurent polynomial ring, a monomial is a unit. A monomial has a multiplicative inverse, so the initial ideal is the whole ring. Right? So the initial ideal is typically the whole ring, as soon as W is random. So that's not so interesting, right? Now that's a big difference to the familiar case, right? If you're in a polynomial ring or you have homogeneous ideals, well then the monomial ideals are very interesting, right? Because the monomial additional ideals correspond to Gröbner bases, and you can do broken circuit complexes and all that, right? Because you have orderings and you have initial monomials. Here, the initial monomial is always 1, because we're in a Laurent polynomial ring. Okay? That's an important difference. So what's tropical geometry then? What's the concern here of tropical geometry? Well, tropical geometry can be thought of as the study of those very, very beautiful special weight vectors W, where this is not the case, right? Where the initial ideal is not the whole ring. Right? So in tropical geometry, we're not interested in these open dense regions. Right? If I pick my W at random and I'm in this open dense region, in the Laurent setting I have an initial monomial that's the whole ring. I'm going to be interested in these white things carved out by my beautiful white chalk, where the initial ideal is not the whole ring. That's what I'm going to be interested in. That is the study of tropical geometry. And this leads to the definition of a tropical basis, 2, 6, 3. Let's look at a finite, and that's important, a finite generating set let's call it now T of I. So I have I is now an ideal in a Laurent polynomial ring over a valued field, and I have a finite set of Laurent polynomials that generates this. I'm going to say it's a tropical basis. Is a tropical basis if the following condition holds. For every vector W in R to the n, if it is the case that there exists a polynomial f, if there exists an ideal element such that the minimum in the evaluation of its tropicalization at W, right? So if we look at the corresponding tropical polynomial and we evaluate at W, that's a minimum of a bunch of things. If this minimum is unique, right, that's a condition. So If you have a W that does that for every f on I, if there exists such an I, if and only if, okay, open parenthesis, if and only if there exists an f in the finite set such that the same condition holds, blah, blah, blah. Okay. Well, that's the definition of a tropical basis. So a tropical basis is a generating set that satisfies this equivalence for every vector W in R to the n. Right? Now, trivially, the first condition implies the second condition. Right? If something is true for every f in the ideal, each of these infinitely many things, in particular it's true for every f in this finite set. So the content is the converse. If the finite set is good enough and big and smart enough to allow for the converse, and if that is true for every W, then I'm going to call calligraphic T a tropical basis. Okay, so that's the definition of a tropical basis. Now, we can phrase this equivalently. So for K, if the field has a splitting, yeah, when we started this, I thought this was sort of splitting hairs, but it's actually important. Right? So it's actually important. There are important fields that don't have a splitting. We have a logic group in Berkeley, and they do, among other things, model theory. Okay? I always believed there's only two kinds of valued fields. I thought they're Puiseux series and p-adics, and that's kind of it, you know? And then you speak to the local model theorists. There are a lot of fields. Okay? There are many, 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 many fields, and they're very unfamiliar and weird, and lots of them don't have splittings. And it's a good idea to keep them in mind. Okay? So, but if K is one of these nice fields that has splitting, this is equivalent to the following condition. For every W in R to the n, the initial ideal is the whole ring, contains a unit, if and only if the initial idea, the n of T, that finite set, contains a unit. Okay. That's equivalent. And I'll leave it for you to think about while you need the splitting, right? So I have the entire ideal, and so this says, you know, if I list all infinitely many polynomials, that one of the initial forms is a unit, right? And this says I can already find a unit by inspecting my finitely many polynomials. Okay? Slightly easier way to state the same thing, and it's equivalent under the existence of splitting hypothesis. Okay. Now, those of you who are here at this time, earlier this week in this room, we had a lecture by Michael Josvik, about a collaborator on tropical bases and the complexity of tropical bases. So that's exactly the same notion, except he focused, in his lecture, he focused on the constant coefficient case. So constant coefficient means you're dealing with ideals where every generator has every coefficient valuation 0. Right? So, and that's just a simplification, but sometimes not an important one. In any case, we have the following theorem, 266. And now there are no hypotheses on the field, so K is any valued field. So this was sort of important to get these results in chapter 2 for arbitrary valued fields to develop, the theory of Gröbner bases and tropical bases at this level of generality. And the theorem is that it says that every ideal I in the Laurent polynomial ring and n variables over this field has a tropical basis, has a finite set that satisfies these conditions. Okay, so that's the theorem. And the way this is proved is by the finiteness of the Gröbner complex. So the way the proof goes is you give me your ideal in the raw polynomial ring, then you pass to the affine closure and to the projective closure. So you have, look at the corresponding homogeneous ideal in one more variables, right? And then for that you have a Gröbner complex. That's a finite polyhedral complex by the main result in the previous section. And then by inspecting each of the finitely many cells of that Gröbner complex, each cell may or may not offer a contribution to the tropical basis T. But by aggregating all of these contributions, you get a finite set of Laurent polynomials that will do the trick. Right? So in the Gröbner complex, there are good cells, those that have chalk, and then there's big bad cells, those that don't have chalk, and you're going to rule out the big bad cells, and you rule those out by a collection of polynomials, and those polynomials then make up the Gröbner basis, the tropical basis. Now, how to compute it? How to compute the tropical basis? Well, it's not easy. Right? So what I just described to you involves the Gröbner complex, but that's also hard to compute. So these objects that I'm describing here are not easy to compute. Luckily, there is GFAN, so there is software you can use, but even in fairly simple examples, these are not so easy to compute. So this means it requires practice. Please practice. Right? So I know there's a study group emerging. Just practice. Right? So tropical geometry, like playing the violin or riding a snowboard, requires practice. Right? So if somebody gives you a violin for the first time and tells you that this object produces beautiful music, and you try it out, you'll be very disappointed. It will not make beautiful music. What it requires is a little bit of instruction and a lot of practice. So Gröbner bases and tropical bases require that kind of practice. Example is if we have a principal ideal, then that's not too bad, right? So if you have a principal ideal, then the singleton is a tropical basis. So then the singleton will do it, right? So you just take F itself. This is a tropical basis. Now, another thing about this, when I first started working in this subject, these things were unfamiliar to us. We were familiar with Gröbner bases. We were also familiar with universal Gröbner bases. So universal Gröbner bases are those that simultaneously work for every term order. And the first version of the first paper, we stated the theorem that says every universal Gröbner base is automatically a tropical basis. So we had this idea that there should be a concept of tropical basis. Only problem was the theorem is false. In fact, Michael Josvik gave a counterexample to this, but we didn't know this, right? So then we fixed it in the second version of the paper. So we started out with this. These were all fairly unfamiliar things, and we made a couple mistakes along the way. In the meantime, they're all fixed, but that, rightly so, inspired Diane on, insisting on precision and correctness. So yes, I agree that, precision and correctness are tantamount to being a mathematician, even though in the initial early stages there might be phases where you make mistakes as you develop these concepts. Let's do an exercise. 21, so we're in two variables. And let's look at the linear ideal x plus y plus 3 and x plus 5y plus 7. So that's an ideal in a polynomial ring, or it's certainly also in the raw polynomial. It's a maximal ideal. Right? This is a really nice ideal. It's a maximal ideal in a polynomial ring. And for consistency, let's take the raw polynomial ring. And the question is this a tropical basis, or how do you compute a tropical basis? Right? So this is a fairly simple, object. Now, okay, well, is this a tropical basis? Now, simple examples like this will be very helpful in going back and studying the definitions, right? So the definition is that, well, K has a splitting, right? Certainly C has a splitting. This is the trivial, this is the constant coefficient situation. The value group is just 0, right? There's certainly a splitting. So the condition is that for every W in R2, for every way of giving weights for X and Y, the initial ideal should be the whole ring. Initial ideal contains a monomial if and only if, the initial of tau contains a unit. Okay? Well, let's maybe try something, right? So how about, this variety is very simple. It's a point, right? So what's the point? It's a point, right? So this is a point in the plane. But let's try, for example, W equals, how about 0, 1, right? Well, the initial form, here the field is the same as the residue field, right? For these weights, the initial form here is x plus 3. That's not a unit. Here the initial form is x plus 7. That's not a unit, right? So therefore, this condition is false. Right? But this condition I claim is true. Right? So I claim there exists an element in the ideal such that the initial form is a unit. Right? So what is this magical thing? Now we have to do some algebra. We have to actually do some non-trivial algebraic operations. Let's take the difference of these two polynomials. Right? That's certainly in the ideal. So if I take the second polynomial minus the first and divide by 2, I get x plus 2. Right? So x plus 2 is in the ideal. But what's the initial form? Well, the initial form is 2. Now that's a unit. Right? So we conclude that this set is not a tropical basis. Right? Because, not a tropical basis because this condition holds, but this condition fails for that t. But it also gives us a hint. Right, how to enlarge this to a tropical basis. We have to throw in additional polynomials in a kind of Gröbnerian way. And this example, you do the obvious thing. You eliminate x, you eliminate y, and it will make a tropical basis. Linear ideals are a wonderful terrain to practice these things because linear ideals are given by matroids, and matroids, you will discover that for linear ideals, the circuits, the linear forms of minimal support, will be a tropical basis. And that's an example. Okay, so that's it. That's the end of chapter 2. So we did two things so far. We gave the tropical islands a glimpse in chapter 1, a sort of welcoming chapter. In chapter 2, we progressively moved from basic algebraic and polyhedral definitions to a more systematic development of these Gröbner on tropical bases. And then next time in chapter 3, we're going to be ready for the heart of the theory, which is the fundamental theorem and the structure theorem. And time for questions. Yeah, so the question is, in the usual Gröbner bases, the choice of term order makes a big difference, right? So there's a notion of term order, reverse lexicographic versus purely lexicographic, and there are big issues of complexity. Can we do the same here? Well, the answer is yes, right? So this choice of the term order really here corresponds to the choice of the where you are in R to the n, right? So basically, you have a given data, which is just coming from the valuation of the coefficients, but then you pick the W. You can pick the W here, reverse lex over there, or maybe you can put it down there in pure lex, and it will make a big difference, right? So you have the Gröbner complex made up of lots of cones, some with chalk, some without chalk, and positioning yourself in this space. Choosing the various cells of the Gröbner complex, that's exactly the difference that it makes. So the structure is the same. You do secretly have these term orders, but we're coding them in the structure of the valuations and the polyhedra that describe these valuations. We're packaging it a little different.
And each region has some advantage which you could actually quantify?
Each region has an advantage or a disadvantage, exactly. So for example here, right, when you do a calculation, you do what you do in your first linear algebra group. You have to either choose, you have to decide, does x come before y or does y become before x, right? So here I eliminated x first and I got something in y, but I could have also done the opposite thing, right? So if you choose the ordering of the columns in a matrix as you do row operations or choosing, that choice is now taken over by the W and by the valuation data. But that is a choice you have, yes. Now this version of Gröbner basis is implemented. So there is a Macaulay 2 implementation. A former student, I think Andrew Chen of Dan Maclagan, made a first implementation. In the meantime, there's a very good team in France that develops p-adic Gröbner bases even more professionally. So there are versions of this implemented. The number theorists like to do this in the setting of the Tate algebra. So non-Archimedean geometers have their version, the Tate algebra. So in the meantime, this version is developed also in terms of software. Yes, so do you have upper semi-continuous? Yes, exactly. You have the same kind of statements, right? So you have the same kind of flatness statements, and you have sort of limits in the Zariski topology. But you have to be a little bit careful, right? Because now you're working in the setting of the valued field, right? So remember, you have R, the valuation ring, as a local ring. So basically, you're dealing with spec R, right? So spec R has 2 points, right? It has an open point, has a dense point, and a closed point. And what's happening over the big field is sort of the fuzziness over the open point, and flatness means you're traveling towards the closed point, right? Which is a spec over K, right? So in p-adic geometry, you have the rational numbers over here, but then you have the reduction mod P over there. And in that sense, we have flatness. Okay. Thanks a lot. See you soon.